lecture series on computer organization and architecture. We'll discuss lecture number 29 of module number 3. Contents covered in the previous lecture are simultaneous requests. Under simultaneous requests, we have discussed daisy chain mechanism as well as combination of daisy chain and priority mechanism. So whenever a multiple IO devices request and interrupts, so how it can be handled. So that is with the help of a daisy chain mechanism. So in order to overcome the problems occurred in daisy chain as well as priority mechanism, the combination of priority mechanism as well as daisy chain mechanism was discussed in the previous lecture. Contents covered in this lecture are controlling device requests. So that is, in this lecture, the objective is to understand how a multiple IO devices, when generating an interrupt request, needs to be controlled. So whenever the devices are not involved in the program, so those IO devices has to be ignored. So those things we are going to understand in this lecture. Learning outcome. After this lecture, the students will have a better understanding of controlling device requests from the IO devices or from the ideal IO devices. So this is the Bloom's taxonomy pyramid. So wherein we are going to understand in this lecture the concepts of controlling device requests from the ideal devices. So hence it is going to fall under the taxonomy level number 2. So we know that whenever an IO device becomes ready, so it is going to generate an interrupt request. So for example, whenever a SYN flag in the status flag becomes equal to 1, automatically an interrupt request will be generated by an IO device. That is when an IO device becomes ready. So it is very much important to ensure that so only the devices or those devices that are used in the program need to be allowed to generate an interrupt request. So the other devices which are idle devices, those devices should not be allowed in order to generate the interrupt request. So even though the IO devices are ready to generate an interrupt request, so those IO devices should not be allowed to generate an interrupt request. So because even they may be ready to participate in the IO transfers. So that is, it is required to control which devices are to be allowed to generate an interrupt request, so and which should not be allowed to generate an interrupt request. So therefore, in order to allow as well as in order to not to allow an interrupt request from a particular IO device, so it can be done with the help of an interrupt enable bit. So here, so we are going to make use of an interrupt enable bit in the device interface. So if the interrupt enable bit in the particular device interface is set to 1, then the device is allowed to generate an interrupt request. So suppose if the interrupt enable bit is equal to 0, then that particular IO device is not allowed to generate an interrupt request. So therefore, an interrupt enable bit in the device interface circuits determines whether the device is allowed to generate an interrupt request or it is not allowed to generate an interrupt request. So why this has to be done? Because so we will be involving only those IO devices that are used in the particular program, and rest of the IO devices, even though they are ready to participate in the IO transfer, should not be allowed for generating an interrupt request. So only those IO devices that are concerned to that particular program needs to generate an interrupt request. So hence we are making use of a particular special bit called as an interrupt enable bit. So if that interrupt enable bit is equal to 1, then that particular IO device is will be given an option to generate an interrupt request. If at all the interrupt enable bit is equal to 0, then that particular device will not be given a chance to generate an interrupt request. So by this mechanism, we can either allow to generate an interrupt request, or we cannot allow, or the option is not provided to generate an interrupt request. So now we know that interrupt enable bit is available in a processor status register. So or else the priority structure of the interrupts can be interrupts determine whether a given interrupt will be accepted or not. So now for example, if you consider a keyboard interrupt enable KEN and display interrupt enable DEN flags in the register called control. So if either of the flag is set, the interface circuits generate an interrupt request whenever the corresponding status flag in the register status is set. So now we have a particular register called as data in, data out, status as well as control. So data in and data out are the registers that are going to carry a particular character or particular 8-bit of information, so that needs to be transferred between keyboard to processor, that is data in register. From if a data needs to be transferred between processor and display device, we are going to make use of a data out register. Along with these two registers, we have two more registers called as status register as well as control register. In a control register, the bit number 2 as well as bit number 3 is relevant to an enable bit. So that is KEN and DEN. So KEN is relevant to keyboard enable bit and DEN is relevant to display enable bit. So if at all KEN bit or DEN bit is equal to 1, then it is, that is keyboard or display device can generate an interrupt request. So in provided, so SIN and SOUT flag, so they are with respect to keyboard and display device. So if the particular bit is equal to 1, it indicates that device is ready for data transfer. And KIRQ and DIRQ are the two bits relevant to keyboard and display device. So if that particular bit is set, it indicates that interrupt request is generated. So enable bit, it is, if it is set to 1, that it indicates that the device is allowed to generate an interrupt request. So if the interrupt request is generated, then IRQ bit will be set. So this is regarding status and control flag. So here we are considering keyboard enable, interrupt enable KEN and display interrupt enable DEN flags in the register control. So if either of this flag is set, then interface circuits generate an interrupt request. So if any one of this particular enable bit is equal to 1, then interface circuits can generate an interrupt request whenever the corresponding status flag in the status register is set. So status flag indicates SIN and SOUT. So SIN and SOUT becomes equal to 1 whenever an IO device becomes ready. So SIN flag, SOUT flag will be equal to 1 when either keyboard or display device becomes ready for data transfer. Enable bit is dedicated whenever the particular IO device is involved in the program. So if enable bit is equal to 1 indicates that those IO devices are involved in the program, hence they can generate an interrupt request. If at all an interrupt request is generated, then IRQ bit will be set. So here, if either of these flag is set, the interface circuits generate an interrupt request. So whenever the corresponding status flag in the register is set. So now, as I told, at the same time, whenever an interrupt enable bit is 1, then the interface circuit also sets the bit KIRQ or DIRQ. So KIRQ indicates keyboard interrupt request or display device interrupt request to indicate that keyboard or display unit respectively is requesting an interrupt. So if an interrupt enable bit is equal to 0, then the interface circuit will not generate an interrupt request regardless of the state of the status flag. So that is, whenever an enable bit, that is KEN or DEN, when these two particular bits are equal to either of these two bits are equal to 0, so even though SIN flag and SOUT flag, they might be set to 1, So even though they are ready, that is even though the IO devices are ready, so IO device can become ready at any time. So even though they become ready by setting a SYN flag and SOUT flag, so they can be involved in the generation of interrupt request, or they cannot be involved in the generation of an interrupt request. So thus so it is a responsibility of the control bit whether to involve this device for generating an interrupt request or not. So therefore we are making use of an interrupt enable bit. So even though the IO device becomes ready by setting a SYN flag or a SOUT flag, so they can be either they can be involved in generation of an interrupt request, or they may not be involved in the generation of interrupt request. So now who is going to control it? That is nothing but interrupt enable bit. So if an interrupt enable bit is equal to 0, then interface circuit is not at all going to generate an interrupt request regardless of the state of the status flag. So no doubt, regardless, it may be SYN flag and SOUT flag may be ready, or may be equal to 1 or may not be equal to 1. So ultimately it is not at all going to generate an interrupt request. Why? Because interrupt enable bit is equal to 0. So if at all interrupt enable bit is equal to 1, then it indicates that the IO devices are essential and they are involved in the execution program. Hence it must be, then hence that particular device can generate an interrupt request. So keeping in that, interrupt enable bit can be set to 1. So therefore, so the second point says that if an interrupt enable bit is equal to 0, the interface circuits is not at all going to generate an interrupt request regardless of the state of the status flag. So to summarize, we are going to consider two mechanisms. So now the thing is that we are going to control an interrupt request. So that is which particular device needs to generate an interrupt and which should not. The one device which is involved in the program can generate an interrupt request. Ideal device, even though they have become ready, they should not generate an interrupt request. So now how to control which particular device should be able to generate an interrupt request and which particular device should not be able to generate an interrupt request. So therefore we have an independent mechanism in order to control the interrupt request. So that is, even though the status flag, SYN flag and SOUT flag, they may be 1 or they may not, anything it might be. So we can control the IO devices generating an interrupt request. So therefore we have two independent mechanisms in order to do this. So one is at the device end and another one is at the processor end. At the device end, we have an interrupt enable bit in the control register to determine whether the device is involved, whether the device is allowed to generate an interrupt request. So say for example, if your program is consisting of keyboard and display device, so you can set a KEN bit or DEN bit. KEN bit and DEN bit in the control register can be set to 1. So if at all you are using keyboard and display device in your program, so keeping these two bit is equal to 1, it indicates that at any given point of time the keyboard or display device can generate an interrupt request. So it can generate an interrupt request. So when they can generate an interrupt request, as soon as they are capable of whenever they are capable of transferring the data between processor and IO device. So that is a SYN flag and a SOUT flag. So as soon when a device generates an interrupt request, it will be indicated to the processor with the help of an IRQ flag. So IRQ flag is interrupt request flag. So therefore at the device end, we have an interrupt enable bit in a control register determines whether the device is allowed to generate an interrupt request. So we need to concentrate on KEN bit and DEN bit if at all in our program we are using keyboard and display device. So if this bit is equal to 1, then we will be involving to generate those two devices in order to generate an interrupt request. So simultaneously we might be having many IO devices connected to the processor. So making all those IO devices particular enable bit as 0, they are not going to generate an interrupt request. Why? Because for the current program we are not interested in those IO devices, hence then no need of those IO devices generating an interrupt request. So hence you can make those IO devices enable bit as 0. So hence we have a control at the device end also. So at the device end we have a control over the IO devices. So now similarly the another mechanism is at the processor end we have an controlling mechanism, so whether to accept that interrupt request or not. So many IO devices will be involved. Yes, so another end we have an option, at the other end we have an option, that is at the processor end we have an option. Even though many number of IO devices might be generating an interrupt request, the processor is going to make a decision whether to accept that interrupt request or not. So when it is going to accept the interrupt request, so it is going to making use of an interrupt enable bit. So either an interrupt enable bit in the program status register. So if the interrupt enable bit is equal to 1 in the program status register, then interrupt request will be accepted by the processor, or else it can make use of a priority structure. So priority mechanisms can be used to determine whether a given interrupt request should be accepted or not. So one is at the device end and another one is at the processor end. So at the device end we will be checking for the control register for the corresponding enable bit, and at the processor end, so whether the processor should accept the interrupt request or not, it will be based upon the enable bit. So whenever an enable bit is equal to 0, even though many number of IO devices might be generating an interrupt request, the processor is not at all going to accept the interrupt request from any of the IO devices. Or the another mechanism is it can make use of a priority mechanism or priority structure, assigning a depending upon the priority level assigned for each of the IO device, it may accept. So if the IO device having a highest priority can be accepted by the processor, and IO priority assigned for any of the IO device is of a very low, so then that particular IO device may not be accepted. So this way we can control the device request. So now let us consider one simple example or a program. So how what are the steps that are involved, that is when to enable a particular bit and when to disable a particular bit. So that is when a program is executed, that is accepting an interrupt or not. So now let us consider a processor that uses the vectored interrupt scheme. So where the starting address of the ISR interrupt service routine is stored at a memory location INT-VEC. So now consider a processor. So that processor is making use of vectored interrupt scheme, vectored interrupt mechanism. So wherein whenever an IO device sends a 4-bit special code to the processor via a data bus, it indicates that it has to give a service for that particular IO device. So wherein the beginning address or starting address of the ISR program or interrupt service routine is available in a particular memory location. So with respect to our example, the beginning address or starting address of the ISR is stored at a memory location INT-VEC. So if I go to the memory location INT-VEC, I am going to get the beginning address or starting address of the ISR program. So that is for the generated interrupt, so I can give the service to that particular processor, particular IO device, that is the processor can run the ISR. So now interrupts are enabled by setting to a 1 an interrupt enable bit IE in the processor status word. So now the processor needs to accept the interrupt request from the IO device. So if it wants to accept an interrupt request from an IO device, so the first thing is that interrupt enable bit must be equal to 1. So if IE bit is equal to 1, then it can accept the interrupt request. So IE bit is available in the processor status word. So it is a 9th bit in the processor status word. IE bit is the 9th bit in the processor status word. It should be set to 1. Now let us assume the devices that are involved in the program are keyboard and display unit. A keyboard and display unit connected to this processor have a three register. One is called as status register, control register, and a data register. In a status register, we have SYN flag, SOUT flag, KIRQ, keyboard interrupt request, DIRQ, display interrupt request. In a control register, we have enable bits of keyboard as well as display, and we have a corresponding data register. Assume that at some point in a program called main, we wish to read an input line from the keyboard, and whatever the input we are going to read it from the keyboard needs to be stored, that is the set of characters needs to be stored in the memory location, successive bytes of memory location. The beginning address of that memory location is called as line. So the objective is, while executing the main program, so as we are involving in the main program, we can involve two devices. So one is keyboard and another one is display. Whenever you are considering two IO devices to the respective program, so in the main program, our wish might be, so one line, input line can be read from the keyboard. So whatever we are going to read it from the keyboard, it needs to be stored in the memory. So the beginning address of the memory is line. So now, in order to perform this operation, it requires to use of interrupts. So we need to initialize the interrupt process as follows. The first thing is that, so whenever we wish to read a line from the keyboard, so it is required to run the interrupt service routine program. So therefore, interrupt service routine program beginning address is available in the memory location INTVEC. Now, that is, the first point says that load the starting address or beginning address of ISR in the memory location INTVEC. So second point says that load the address line in a memory location PNTR. The ISR will use this location as a pointer to store the input characters in the memory. So now PNTR is a pointer, so that thing will be used by the ISR program in order to store the characters that is being read from the keyboard in order to store it in the memory. So now enable keyboard interrupts by setting bit number 2 in the register control to 1. So why? Because third point says that interrupt KEN bit must be set to 1. So KEN bit is available in the control register. KEN bit is available in the control register. It is bit number 2. So therefore, so enable keyboard interrupt by setting bit 2 in the register control to 1. Enable interrupts in the processor by setting to 1 the enable IE bit in the processor status register. See here, KEN is equal to 1 in the control register, whereas in the PS register, IE bit, which is a bit number 9 in the processor status register, should be made equal to 1. So here third point says that we are allowing keyboard to generate an interrupt request. So setting IE bit is equal to 1 in the PSR, that is processor status register, allows the processor to accept the interrupt request from the keyboard. So this is regarding fourth point. So once this initialization is completed, so typing a character on the keyboard will cause an interrupt request to be generated by the keyboard interface. So whenever an IO device, that is keyboard device, becomes ready, so if I keep on typing the character, automatically the interface circuit is going to generate an interrupt request to the processor. So the program that is being executed at that time will be interrupted. So the currently running program will be get interrupted, and the ISR program needs to be executed. The ISR program should be capable of accepting the characters that has been typed from the keyboard. So that is, this routine has to perform the following task. So what it has to do, that is ISR program. So whenever a keyboard device generates an interrupt request, then currently running program needs to be stopped and ISR program needs to be executed. So what is that ISR program? What it is going to do now? So the ISR program is going to perform the following task. What are the following tasks is, the first thing is that it is going to read the input character from the keyboard, and it is going to place that character in the interface circuit, that is in the data register. So every IO device will be having a register. So the character that is read from the keyboard will be stored in the register. So this will cause the interface circuit to remove its interrupt request. So now after reading a character from the keyboard, the next thing is that it is required to store that character in the memory location. So memory location line will be pointed by the PNTR. So every time whenever a character appears, so the character will be dumped into the memory location, automatically the pointer gets incremented. So when one full line is reached, when the end of the line is reached, it is required to disable the keyboard interrupt and inform the main program. That is, reading one full line of character is over, so hence nothing to do with the keyboard. So that is, the processor has provided the service for that keyboard, so hence it has to go back to the main program. So therefore, as soon as the end of the line is reached, it is required to disable the keyboard interrupt and execution of the main program has to be done. So therefore, it is going to inform the main program, so hence it is required to return from the interrupt. So that is, it should after execution of the ISR, it should go back to the main program. So thus it is required. Fourth point says that it is required to return from the interrupt. So now here we have a program. So what are the initialization we have to do? So as I am going to execute the main program, first thing is that memory location, the address line needs to be stored in the pointer. So I have to clear EOL. So EOL indicates end of line. So end of line indicates that the sequence of characters, one line character will be read. So after that end of line is completed, so we need to stop reading the character from the keyboard. So therefore here initially whenever end of line is reached, automatically end of line becomes equal to 1. So therefore right now we have not read any character from the keyboard, so hence it is required to clear the end of line. So EOL becomes equal to 0. I have to means keyboard needs to generate an interrupt request. Why? Because I am involving in my program, I am involving keyboard device. So if I am going to involve a keyboard device in this particular program, I have to keep enable bit is equal to 1 with respect to the keyboard. So therefore it is required to set bit number 2 in a control register. So bit set #2, control. So it says that control in a control register, bit number 2 needs to be set to 1. Similarly, a processor needs to accept the interrupt request generated by the particular IO device or from the keyboard. So hence program status register, in a program status register we have an interrupt enable bit. It is a bit number 9 in the program status register. So therefore it should be set to 1 if at all a processor needs to accept the interrupt request. So hence we need to set the next instruction is bit set #9, PS indicates that program status register bit number 9 becomes equal to 1, which is nothing but interrupt enable. So now initial setting is over. So now while executing the main program, so it may be in the middle, it may be it may be required to read a character from the keyboard, sequence of characters or one line characters from the keyboard. So therefore interrupt service routines starts to execute. So here certain set of registers are stored onto the stack. So pointer will be stored onto the R0 register. So read a character from the data in and store it in a R1 register. So from R1, R0 is going to hold the pointer. So there you can keep on storing it into the memory location, that is PNTR. We are using auto increment mode. So after reading all the character, so store that content of R0 register to PNTR back. So now check out whether the read character, last character read, is a carriage return. Is it equal to content of R1 register? So if it is not equal, then again you go back to same thing. Else if the things are that is if branch is not equal to 0, you can go to return. So otherwise we need to set certain things. End of line becomes equal to 1 and control register becomes equal to 0. Bit clear means make the control register bit number 2 as 0. So finally you can pop up the things and return from the interrupt. So now it says that when the end of the input line is detected, the ISR routine clears the content of KEN bit in the control register as no further input is expected. It also sets bit number 1 EOL, that is end of line variable. So this variable is initially set to 0. We assume that it is checked periodically by the program. So main means we are going to keep on checking EOL whether it is equal to 1 or it is equal to 0. Periodically it will be checked. So main to determine when the input line is ready for processing. So conclusion is we have discussed controlling device request. So that is we will be concentrating on two things. One is the devices that are relevant to the program. Only those devices that are relevant to the currently running program can generate an interrupt request. So other IO devices or other ideal IO devices, it is not required to generate an interrupt request from such kind of an IO devices. So hence it is required to control those IO devices generating an interrupt request. So therefore we have a mechanism so wherein we can allow the devices to generate an interrupt request or not to allow. So hence we will be concentrating on an enable bit. So if at all an enable bit in the if the enable bit of the corresponding IO device is equal to 0, it indicates that that particular IO device cannot generate an interrupt request even though the device is ready by setting the status flag in the status register. Whereas in other case the other thing is that if an interrupt enable bit is equal to 1, then that IO device can generate an interrupt request. So if the device is generating an interrupt request, then corresponding IRQ bit needs to be set. So similar parallel, so this can be done at the device end. So same thing can be done at the processor end also. So the processor may accept, may not accept the interrupt request generated from the IO device. So if it wants to accept an interrupt request, then automatically it is going to set the interrupt enable bit is equal to 1. That is the processor register will be set to 1. Processor register interrupt enable bit will be in the processor register, interrupt enable bit becomes equal to 1. So if it is equal to 0, it is not at all going to accept any interrupt request, or else even it can accept the interrupt request based on the priority. So these concepts are discussed in this particular lecture.